Our next speaker is Dr. Joseph Simonian. He is the founder and CIO of Autonomous Investment Technologies in Newton, Massachusetts. AIT provides AI and machine learning consulting services to the financial industry and builds custom quantitative models for financial firms. Over the past 15 years, Joseph has held senior portfolio management and research positions in several asset management firms, including the Texas Asset Managers, Fidelity, PIMCO, and JP Morgan Asset Management. Joseph is a noted contributor to leading finance journals and a prominent speaker at investment events worldwide. He is currently the co-editor of the Journal of Financial Data Science and is a member of the editorial board of the Journal of Portfolio Management. Also, I have the pleasure of working with him as a member of advisory board of the Financial Data Professional Institute. Joseph is the author of over 40 academic publications, and he has vast experience in teaching both in academia and industry. He holds a PhD from University of California, Santa Barbara, an MA from Columbia University, and a BA from UCLA. We are honored and grateful that he has accepted our invitation to speak to us about machine learning and asset management and the role of econometrics. Joe, thank you.
Sure.
Thank you.
Okay, so I started to think to myself, is there a fourth way, really? Is there a way where you can actually, within one framework, in other words, not say, let's use a regression for this project, but let's use a neural network for this project, but develop a way of actually incorporating both types of cultures or frameworks, within a single approach, right? So that econometrics or traditional statistics can add value to the actual data science approach or framework that you're using to execute another part of the project, right? So kind of a more of a unified framework. Now, why do I even have to think about this, or where does this even come from, right? So there's a famous paper that most of you are familiar with by Leo Breiman about the two statistical cultures, right? And he refers to the data modeling culture, which he talks about, represented by kind of traditional statistics. In finance, I think it's represented by econometrics. And then, the algorithmic modeling culture represented by data science. So, data modeling, is predominant in both, finance and natural science. And it's really concerned about providing, assuming that there is an actual process underlying what you're trying to model and trying to figure out what the relationships are within that process. I'm just kind of simplifying it, but that's essentially what it is, right? The algorithmic modeling culture, on the other hand, doesn't really assume that there's anything really going on. It's more of a just, let's see if we can actually make predictions and discover patterns. And Breiman's point, he's a brilliant guy. He's passed on now, but he was one of the co-founders or co-developers of Random Forest, and he's done a lot of other great things in his career and his life for the field. But his view was essentially that if you're a practical person, and he had left academia for a while, and he'd been a consultant, you have much more affinity toward the algorithmic culture versus the data modeling culture, because you want to get results, and those results are often predictive results. And so, as a consequence, in recent years, as the technology and the computing power has gotten better, because in finance, we're primarily concerned with predicting, right? I mean, alpha is generated by forecasting successfully, in simple terms, right? These techniques are of interest to us. But that said, traditional quantitative investing has not really been aligned with the algorithmic modeling culture. And there's a historical reason for that. So if we take a trip down memory lane, if you will, the methodological foundations of contemporary econometrics were by and large laid by the Cowles Commission in the 40s. And think of people like Koopman and Havelmo, right? Maybe he has that very long probabilistic foundations of econometrics paper that was, the entire paper comprised the entire issue of Econometrica, right, when it came out, so long. Right, so the idea with the Cowles Commission members was that you can't really interpret data, economic data, properly without a very well-founded, well-hewn theoretical construct underlying it. Right, so the emphasis was on theory, not really forecasting and measurement. Now, at the time, there were rivals like the National Bureau of Economic Research, which still exists here in Massachusetts, and they were much more oriented towards, devising measurement techniques, more of an empirical stance, if you will. And a few years later, there's the famous paper by Friedman, on methodology, which is one of the most famous papers in economics methodology. But I would argue it's also one of the least followed, and that's not because of the paper is bad. I think it's a wonderful paper, actually. I just think that essentially what Friedman argues for in that paper, if some of you are familiar with the philosophical school called pragmatism, he essentially approaches economic models in a pragmatic fashion. In other words, they're basically tools for making successful predictions. And a theory or theoretical assumptions really serve no purpose beyond that, right? It's really to get things done, right? And if you can't get things done with a model, it's basically useless. Okay, and so what happened was the end result was, as econometrics developed, and financial econometrics as well, we've developed a suite of what I consider mathematically rigorous yet predictably often very weak models. Okay, I can give you an example. So I wrote a paper in JFDS called Minsky versus Machine, where I presented a data science oriented approach to regime switching and actually macro investing based on regimes, but in stark contrast to sort of the Hamilton style regime models that we're familiar with. Now, that's not to besmirch that model as a device for explaining the past, but we all know, and I mentioned in the paper, sort of a dirty secret on Wall Street is that, a lot of people talk about regimes in casual conversation. Many teams often end up building regime models, but very, very few teams actually trade using traditional regime switching models. And the reason is because they have an extremely poor predictive track record. And if you don't take my word for it, there have been papers written by many, many people, including people like Bob Engel, that attest to that fact, that they really have but very weak predictive power relative, I would say, to the technical complexity and the effort you have to put into actually building one of these models, right? Especially if you're using a more expansive set of factors, if you've got more than two regimes, right? Anybody of you who has built one of these models, and I have 15 years ago, sort of to productionalize it in a firm, realizes how onerous it can be. And when the end result is very little, you kind of feel let down. I actually liken a lot of econometric models to Rube Goldberg machines, which are, Rube Goldberg was a cartoonist who drew these elaborate contraption devices that did a very simple thing, like pour water into a cup, right? And, a lot of econometrics to a practitioner often seems that way, right? And so I think on the predictive front, there's clearly a need for data science. But that's not to say that econometrics is not useful. So traditional statistics, like even an OLS regression or regime switching model or vector autoregression, whatever you want to use, they're very good at carving up the world, right? You take the past, a sample, and you say, why did certain things happen, right? And that involves, assumptions, but it also involves, a heavier use of probability theory. And you often get a very satisfying picture of the world as it was, okay? Now, going forward, though, I think that's where sort of its utility drops off. And in terms of making predictions, that's where I think a lot of data science has to come into play, or machine learning, to help us in terms of signal generation and so on. But now the last point here, are they mutually exclusive? And my answer is no, and I'll tell you why. So, I'm a fan of what I call statistical multiculturalism, right? So again, one of my brilliant terms. So modular machine learning, essentially, it's a framework where, you have, as the name says, a set of modules. And each module is devoted to either an econometric framework or model, or a machine learning and data science model. Now it's modular because, well, I say here, so it's modular because, first of all, there are independent modules, each devoted to one kind of framework, number one. Number two, more importantly, when you start with, let's say, the first module, and then you have output from it, that output directly feeds into the next module. It does what it does, and then it actually generates new output, and then it passes it along to the third module, so on and so forth. So each module is dependent for its inputs on the output of a preceding module. So it's truly modular in that sense. Okay. Now let me go back here. Now we're going to talk about this because I have a paper on this where I have an example. And it's just one example. In reality, you don't have to really read the example to start to use the framework. But the example is useful in understanding kind of in a real life example how this could work within a very popular investment model. Okay, the fundamental law of active management. Okay, now one of the things that we have, right? So as financial data scientists, we're often inheriting a lot of math and models from just pure data science, right? And those guys, as brilliant as they are, do not often think in terms of the needs, for example, of investors or economists or financial practitioners. And it's not their fault because they're actually just developing a theoretical construct, and it's the job of the person applying the model to think of these things. And so, for example, things like cross-validation. Now we have time series cross-validation, right? That was invented before finance got involved, but the number of the length of the folds, for example, in a cross-validation is often arbitrary, right? And in reality, that's not necessarily ideal. Number one. Number two, when you have, even let's say you go back 10 years and you say, okay, I'm gonna have a 5-fold time series cross-validation with expanding windows. That's fine, but that doesn't take into account on its own that the economy could have been in, or in the markets could have been in different states all along the way until as you're running the training and the testing and the validation, right? And so right there you can see that a regime switching model has a very natural application in cross-validation, because what you can do is say, look, I've got 10, 15, 20, whatever years of history, and I want to use that to train and test my model. That's fine. But I also want to distinguish between states of the world, because maybe this signal works well in a recession, but doesn't work well in an expansionary period. So I want to know that, right? That's a natural thing that any investor wants to know. When do these signals work, if ever? And what is the efficacy in different states of the market or the economy? And so naturally, you could apply a regime switching model, carve up the world and history in that way, and say, okay, great. I'm going to use these as my folds for my recessionary cross-validation. I'm going to use these as my folds for my expansionary cross-validation. Now, that does two things. One, it tells you, okay, which observations to use, but also the fold length is also determined by the model itself, because it's going to tell you how long each regime lasted, right? So you can very confidently understand you can sort of marry the data science to economics in the real world, in a sense, right? Because you're understanding, let's test this signal in this state of the world and versus that state of the world. And again, a regime switching model, for example, among many other models you could use, could carve out the world very effectively like that. Now, there's another thing that happens when you do a time series cross-validation, right? Which is that often there's a memory, right? So you have a training set and you have a validation set, and you make that cutoff, and you basically train in one and you validate or you test on other samples, right? But if there's just a straight handoff, if you will, from training to validation, there's often a memory between the end of the training period and the beginning of the validation period. Okay, so something has been developed, by data scientists called block time series cross-validation, which inserts, right, a number of observations in between the two, and those they drop out. So in other words, it allows the validation set to forget, if you will, what happened in the training set. Now, a natural question is, how do you determine the block size, right? Because it's also typically arbitrary. And again, not the fault of the data scientists who came up with this, but for us, we have clearly an idea of memory and time series and financial time series in particular. And so you have to wonder, where do you get that from? Now, a regime switching model by itself also provides that information, right? Potentially, because every regime switching model assumes a process that has an autoregressive order of a certain value, right? Well, that more or less straight away means the time it takes for each regime to forget, or within a time series, the length of time in which the time series itself forgets what happened, right? So you can easily take that autoregressive order as the block size and construct your cross-validation in a very economically, if you believe your regime switching model, in a very economically, loyal way, if you will, right? True to what is happening on the ground in the economy can actually influence the model validation process itself. So I think that's a very nice and elegant way of actually not trying to force a regime switching model, for example, into doing something it's not supposed to do, which is predict, but actually utilizing it in a way that fills gaps within the traditional cross-validation approach or modeling exercise. Okay, so that's essentially what we're doing. Now, I should say I use regime switching in this. I think I use the paper Falardo's model, which allows you to posit an exogenous factor, but you can use, there's so many out there that you can use whatever you want. And I think this is not limited to regime switching, but this is the example I used. But you can use other kinds of traditional statistics or econometric techniques to essentially frame the world and understand it, and then do the validation, cross-validation, or model validation based on your understanding of the world, right? Which is very important because, again, a lot of the textbooks, they're purely statistical, right? They each epoch or each episode or each what have you subsample is treated more or less the same, at least if you go by the traditional machine learning books. And that's understandable given that in natural science, data is quite a bit more uniform and homogeneous relative to finance, where you've got a lot of things going on, a lot of dynamics that can actually have relevance to the efficacy of a specific model. Okay, so the case study. So now we move on to the fundamental law of active management. So it's a well-known way of characterizing portfolios managers' alpha generation process. Now, it's typically used as a way of decomposing alpha, right? So, understanding, how many views or bets were injected or used in a model, the actual effectiveness of each of those views or bets or positions, right? But I thought about actually refashioning it into a way of actually doing model validation. Now, before we get to that, we have to understand that, which fundamental law, because over the years, there have been several incarnations of the fundamental law since Grinnell introduced it in '89. I believe he introduced it. So I use a version that's provided by Yi. It's 2008, the version of this. And the reason I like it is that it's relatively simple, but it has a little bit of, there's some interesting aspects to it for primarily that it includes the variance of the IC, which is the information coefficient, right? These are, the information coefficient is often taken to be the Pearson correlation between a signal or a view and the excess returns, right? So, in other words, how effective was your view is measured by the IC, okay? And so this is relatively simple, but it has that variance, right? Because we want a relatively stable, we would think we want a stable signal, okay? So we use the Fama-French factors in our example, right? Plus an asset's 1 month lag returns, kind of an AR1, kind of a primitive momentum factor. And we essentially run it. Now we have 3 modules in this example, okay? So the first is this, what I call the subsample classification model, which is essentially what I just described with the regime switching. So I won't go into that too extensively because, in the interest of time, but I've already described it. Essentially, we use regime switching to carve the world up and give us the length of the folds and the location of temporal location of the folds, right? But in the paper itself, I also impose 5 folds for each, so we have 2 regimes, contractionary and expansionary. And I said, I'm going to look at the last 5 folds that correspond to each regime. You don't have to do that. You can actually just say, look, I'm going to go back 20 years. And you can, if there are 7 expansionary folds, I'm going to use those. If there are, 2 contraction, I'm going to use those. I didn't do that, but you can do that. You're free to do that in this, right? And like I said, the block size is equivalent to the autoregressive order, okay? So the next, module is what I call signal quality. And like I said, in this module, typically, the IC, you measure the efficacy of the IC with Pearson correlation. I do something a little bit different. So I do separate univariate predictive regressions, block time series cross-validated regressions for each of my factors individually. And then I basically get a predictive score, which is like an R-square, right? And I use that as the final fold value, right? Because it's an expanding window. I use that as the IC for each of the factors. And then for my IC, in terms of my model, if I go back to Yi's formula, I basically just average the final fold ICs for each factor, and I put that in the numerator. And then, then I also calculate cross-sectional variance of the final fold ICs, and I put that as the IC variance. And then that's how I get my information ratio value. Okay, but before I get to that, I need one last step. Okay, which is the I call the signal diversification model, because remember, in the fundamental law of active management, you also have breadth, or NBR. Basically, it's either a measure of the number of positions you have, the number of signals you have, the number of independent views you have, or bets. You can interpret, this has been interpreted alternatively in various ways. But what I do is I try to say, look, I've got 4 factors. Now we've measured their efficacy, right? So their IC value. In other words, how well do they let you predict a certain sector, right? So for example, in the paper, I use the manufacturing sector, one sector. It's just an example, right? And I want to see how well does, let's say, the Fama-French market minus risk-free rate factor help us predict the returns on the S&P manufacturing subsector index, something of that nature, right? Same thing with size, value, and my AR1 factor. So, in other words, if the score is high, the predictive score is high between these factors, and the manufacturing sector's returns, then that would be indication of a high IC. Okay, that's how I interpret it. Now, it may still be the case that let's say all 4 of these factors, they're very good or very bad. Okay, and I'll tell you what happened at the end of this as well. But it may be the case that at least statistically, they're the same signal, they're the same factor. And that's relevant because in the IC, you have to inject the number for N, or breadth. And we have to know in our case, in our example, are you going to insert 4 or 1 or 2 or 3? In other words, are these signals in fact different? Now you may say, Joe, what are you talking about? How is the market factor different from, not going to be different from value or size or what have you? Well, they may be different in terms of, flesh and blood, real world sort of characteristics, but statistically they may be the same. They may be either very effective or ineffective. And my interpretation is that, well, look, if they are doing the same thing statistically, and we have to define that the same thing, and we do that here, then it's not necessarily, it's not clear that they should all be used, because you want to have a model. Remember, the rule of building a factor model is to have a parsimonious model. So if you have 4 factors that are statistically identical, quote unquote, then you potentially want to drop 3 of them and only use 1 of them. You actually want factors that are distinct in their characteristics. So what I do is I use something called affinity propagation. It's a clustering technique. That one of the main reasons I use it is because you don't have to impose a number of clusters, right? It's also useful because it's graph theoretic method, so it's kind of easier to visualize, right? And it basically goes on this idea of message passing, right? So the idea is that information is passed between members of a cluster, or vectors, if you will, or observations, until they realize, oh, I belonged with you, I belong with this one, we're in the wrong cluster, and so on and so forth. It's an iterative process. And what I use essentially is the IC values and the IC variance, but you can use other statistical features as part of your vector as you do the clustering. But I use those 2, and in the end, we essentially get that the market factor is distinguished from the other 3. Moreover, it has, it's really the only factor in this experiment that has any predictive value. Moreover, we found that the model itself, so you take the 4 factors by themselves, really have predictive value only in the recessionary regime, right? So when you do the cross-validation on that state, you will see a positive score. When you do it on the expansionary regime, the scores are negative, which means that it's kind of a random model, basically. Now, in the paper, I'll just close with that. I don't mean for this result to be any kind of final conclusion on the predicted efficacy of the Fama-French factors, because it's a very simple model. The whole point of this exercise is to show how you can go about using both econometrics and data science to actually build a fairly thorough model validation framework that also is economically intuitive, because you can actually interpret why the signals are doing things when they're doing it. So I think in the interest of time, I'll end here, right? I think, and then we'll open it up for questions.
Well, thank you very much, Joseph. Something happened by mistake. I made you host rather than co-host, so basically you have control of the whole conference. But okay. You can give it back to me.
Took later. Over, yeah. Okay. Okay.
All right.
So let me look in the chat here.
Yeah. All right.
Okay. Oh, it's just about co-hosting. Okay, so let's open up the questions that people have.
Sure. Yeah, I have a question. I'll get it started. This use of econometric techniques and machine learning, basically, to improve the prediction of your models, what's the relationship between that and feature engineering? Are we using the econometrics sort of to do the feature engineering part of our
well, that's a good, yeah. So no, we're not engineering the features, right? So the factors themselves are given, but by Fama-French. Now you can do various things. I haven't addressed that in this paper, right, at all, because you can only address so many things in one paper. But basically, like in anything else, you have an ability to either pick out factors that have been tried and true and tested, right, like I did, just to simplify the conversation, or you can actually try to generate or discover factors on your own. So for example, the simplest case is an old school methodology, but PCA, right, is a way of, kind of feature engineering, if you will, because you're taking an initial set of data and then transforming it into a new set of factors, right? So there are, more advanced or more contemporary techniques to do that now, but I don't do that here, but you could do that, right? For example, even within the context of traditional factors, you can, like let's say you're using a random forest, you can dump them in and you can see what the feature importance is of, let's say 10 factors, and maybe you cut off the 5 that are the least important. You can do that. Again, that's more of a factor discovery or factor evaluation or assessment process, but we're not creating our own factors here. No, I think what the econometrics is used for here primarily is to really address the gap that we have in applying data science, let's say out of a textbook, to finance, which is a few of the gaps, right? Which is one of which is that you don't know, you're essentially forced, if you will, to take history without any kind of differentiation between economic states, right? So you're just, even if you're doing time series cross validation, you're just saying, oh, I've got 5 folds or 7 folds or whatever I have, and I don't care if I've got overlapping expansionary and contractionary regimes or high inflation, low, whatever it is. I'm just going to cut the world up like this arbitrarily, 5, 7, 10, whatever it is, and then do my training and a validation that way. What I'm saying is that, as practitioners, we do distinguish between expansionary and recessionary regimes, right? And they matter to us, if you will. And if they matter, they should matter in terms of our model validation efforts, right? And so we need to cut up the world, our subsamples in a way that speaks to that. Now, it doesn't have to be expansionary and contractionary. It can be high inflation, low inflation, other, high interest rate, a falling interest rate, et cetera, et cetera. The point, though, is that if you want to interpret your signals in an economically viable manner, you're going to have to do that kind of an exercise, because unless then you can just say, well, look, here's the score, and you don't know why or where that score came from, because when to use it. So in other words, let's say you believe economists telling, oh, we're, simple primitive example, yield curve, Cam's not here anymore, but the yield curve inverted. Okay, we got a recession coming, right? Well, okay, so what do we do? Well, how do we use these signals? Well, if you haven't cut the world up in a way that you actually understand that, how your signals behave in these regimes, you haven't validated in that way, well, then you don't know if your signals are going to work or not. If they have a high score, you'll just assume that they do, but they may not. Their efficacy may have been limited to one specific economic or market state, and that has to be discovered, right? So that's where I think the utility of these techniques come in, because they help us carve up the world in, both probabilistically, but more importantly, economically intuitive ways, right? Which in cross-validation you don't get by itself. Now, the block thing is also interesting, because that's another nice thing about this. If you buy into the picture of the world that econometrics give you, or let's say regime switching model, where they assume that a process has an order, right? And that order is actually relevant to memory. And that question of, what do you insert as the cross-validation block size to separate validation and training sets, right? So there's a lot, I think, that informational value that traditional econometrics adds in setting up the validation exercise. But then once that exercise is set up, the actual running of the testing has to be done with data science. That's my point.
Thank you so much. I think you kind of answered this partially, but so would this technique be useful in sort of finding what are the variables that define the regime, for example? One can look at the volatility, one can look at other measures of financial distress and so on. Is this sort of can be also used to identify the most efficient way of defining regimes in this case?
Well, it can be, it's a good question. It can be used in the sense of, let's say you run the regime switching model with, let's say, industrial production by itself, like a simple Hamilton kind of a setup. And then you actually say, well, look, we ran it this way and our signals produce these scores, okay, in terms of expansionary and recessionary regimes. And then you run it with, let's say, a Falardo model, and you say, well, we have, industrial production now as the endogenous factor, but we have the interest rates as exogenous factor. And you see that, okay, you cut the world up in a different way. And in that context, your signals actually do better. I think there's some value to be gained there, right? Because then you say, well, look, approaching the world with this worldview, if you will, economic worldview of industrial production plus interest rates is more useful than, industrial production by itself, right? So I think, again, and it's not kind of like, it may smell like it's data mining. I don't think about it that way. I think about it as worldviews, really. It's a German term, Weltanschauung, right? It's how you view the world, what drives the world, right? And let's say in my example, industrial production by itself would be a poorer representation of how the world is than the Falardo kind of setup where you have an exogenous and endogenous factor, and interest rates play their role too, because then you cut the folds up in a way where your signal actually is more effective. And then okay, if we use my signal with industrial production and contractionary and recessionary states, it's not going to be as effective if we look at that, plus what are interest rates doing, right? So on and so forth. So I think that's where the value added here is that you're really gaining from having a very informative or uninformative worldview that's given to you by econometrics. Now, again, when I say econometrics giving it to you, you have to buy into the assumptions of these frameworks. But hey, it's all we have to go on. In essence, all we have is either traditional econometrics or data science. And data science is not very good at kind of telling you the narrative, the story, why something happened, right? It's very good at actually getting the predictive results or the classification or what have you, understanding how the data is structured, but it's not really useful at telling you what are the economic drivers of something. And that's where I think econometrics plays a big role.
Very good. Actually, you kind of anticipated my next question is, people complain about lack of interpretability, or it's a black box, especially when you get to deep learning and so on, and that basically prevents sort of this whole area to penetrate asset management, because institutional investors are not comfortable with having a black box in charge of their fate. So what's your opinion on that? What's your take on that?
Well, I agree. I mean, think about any given model, and let's go back to like a random forest, and you can use random forest to do to solve regression type problems, but you can also use it to solve classification problems. Now, even though the word regression is used, in reality there are quite a few differences in the output. For example, you don't get a beta coefficient, right, when you run a random forest. I actually wrote a paper on this in the first issue of JFDS, where I actually created something called a pseudobeta. Now, I created this only as a communication device, and I specified in the paper, don't use this to trade, but it's just to understand what would the coefficients be if this model behaved like a traditional OLS regression, right? So there are gaps here, right, in terms of, if you come from a traditional statistical background, even the output itself often is the kind of, what do I do with it? Now, there are ways out of it if you actually dig into the results, right? So in that same paper, we recreated a quantile regression, more or less, right, with random forest, and we did a bunch of other stuff. But the point is that you have to give it some thought, right? How do I, so what I think Hussein, to answer your question directly, I think the main gap that happens with practitioners, especially ones that are like sort of, let's call them refugees from data science, they don't have as much finance, kind of background, is that they often, they miss that there are quite vast differences between how the output is presented with traditional statistics and econometrics versus data science and machine learning. What it means is not that they're hopeless or they don't think there's no hope for them. It means that you have to put thought into the communication of results in a way that I think a lot of people haven't done. I mean, it's getting better. I'm just saying in general, that is a gap that I still see, right? And so, so that, but that's evolving, right? So, in that same paper, a lot of the effort is made not only on the technical side, but also kind of relating it to, so not only quantile regression, but we also show how essentially you can actually adapt random forest output to be the equivalent of a sharp style analysis, right? And so on and so forth. So, and then the pseudobeta idea. All of it is to make the traditional finance practitioner more comfortable with this domain, because if it's like any product, right? And a model is a product. If somebody doesn't understand it, they're not going to use it, right? And so I think that more effort has to be made in that area in terms of interpretability and understandability. Now, other things are a little bit more understandable, right? But I think in some cases that is an issue, and we have to work on it, because I mean, I was at a conference. I'm not going to give all the names here, but there was literally a fiasco that happened a few years ago, where somebody got on stage and was presenting basically a horse race, machine learning versus traditional stats, and machine learning wins all the out of sample and what have you, all the tests and cross validations, and traditional statistics stinks. And in the audience were all these old school quants. Many of the names, if I name them, you'll know them, and they're great guys and gals and very educated and awesome and wonderful. Their hands went up, and it was literally attacking the guy, because and I spoke to all of them on the sidelines, and they basically told me, look, he's telling us, giving us output without explaining any way, why anything is happening, right? He's just saying, this is what I ran, and this is the end of the story, and you have to accept it like this. And his only response, and then it was funny, he was pounding the table saying, I'm an empiricist. I made a joke. I said, if you ever end the conference presentation yelling at the crowd saying, I'm an empiricist, it didn't go well. Okay, but the point is that it's a persuasive exercise. It's not an exercise in intimidation or forcing people to use things. It's saying, look, these are actually, at the end of the day, these frameworks are better in our bread and butter business, which is prediction. Okay, and we're going to hold your hand, figuratively speaking, right, in getting you to understand why they're better. And on the way there, if there are things like in this paper, if there are traditional statistical or econometric methodologies that we can actually use to add value to the predictive enterprise, if you will, we will use them. We're not going to let them go. But let's also be honest about, sort of the failings, if you will, of our quant past. For example, PCA, while in some contexts, like yield curve decomposition, is very understandable, in many other contexts, it's incomprehensible. What are these principal components? You have to do additional work to interpret them, and it's often not worth the effort, right? So those are like sort of kind of more old school issues, but I think a lot of data science and machine learning addresses some of these gaps that we had in the old days, if you will. I mean, I'm not that old. I'm kind of a second or third generation quant, but I think that so it's an exercise in understanding what from the old toolbox works, what doesn't, and we got to let that go. And then what from the new toolbox works and doesn't, and we have to utilize what does work better and what doesn't a little bit less. For example, there's deep learning and neural networks are all the rage in many quarters, and they're very useful for some applications. But we have to understand that anybody who knows anything about these models, they're often very input data intensive. And I've had the case where I've tried to build platforms and stuff using these things, where we, and if you're sort of a lower or mid-frequency investor, monthly or weekly data, you often see you get junk output, right? And so, I'm simplifying a little bit, but you understand that you have to pick your poison based on the application and the input requirements of the algorithm that you're using, right? So I guess, I think my biggest beef, if you will, with the sort of traditional way of doing quant is that we also have to recognize that the adding value, managing money is hard. And there's so much information coming at us in 2021, right? I mean, there was a lot coming at us 50 years ago, but even more now, right? That to think that you can actually successfully manage money with a regression-based framework by itself, I think is delusional. But, I think it's being polite even saying that. So I think some of these techniques, have to make their way into almost at least all quant shops, right? In some way or shape or form, but how they get integrated will be different based on the firm and the team. What I see often, though, is that there's just lip service paid to it, and they're just resting on their laurels. Now, you saw that what happens in the end result often is that you had this quant value meltdown, a few years ago, right? Which just got recently better because of some technical reasons in the market. But in reality, I think those firms have to ask themselves, why did we melt down so bad? How did our models fail? And maybe we used a little bit more high-powered predictive framework, could we have done better, right? And if that's the answer is yes, I think they should, maybe start to revise and think about, from the ground up, how they can enhance their frameworks, their investment process. This is for quant firms, right? Fundamental shops, I'm not speaking to them in this respect, but so I think ultimately, obviously, I'm the co-editor of JFDS, and I'm a fan, and I'm a proponent of these techniques, but they have to be used responsibly. That's my basic message. Sorry, I went a little long there, but.
No, great message, great talk. Thank you so much. We are very grateful, and thank you again for taking time and presenting to our conference.
Okay.
So we're going to take about another 15 minutes break, and then we'll come back and we'll hear from